Delaware Tech, Chemistry 100, Chemistry 110, Unit 3, Atoms and Elements, Introduction to the Periodic Table. The periodic table, shown here, is a representation of all of the known elements so far. To date, we have 118 different chemical elements, and each one is numbered from 1 to 118, and each one has its own 1 or 2 letter chemical symbol. The symbols typically are similar to the letters in the name, but there are a number of exceptions because these are symbols based on the ancient names for the elements. And in the case of tungsten, W, the symbol is named after the German name for tungsten, Wolfram. The periodic table is arranged in periods and groups. Periods are the horizontal rows, and groups are the vertical columns. Many of the groups have names, and we'll be talking about those names. And then there's another way to organize the periodic table in terms of 3 general groupings. The metals, which is everything to the left and down from that blue diagonal of elements. The nonmetals, which is everything to the right and up of the blue diagonal. And the metalloids, also known as the semimetals, which are the blue diagonal of elements. We'll talk about the early history of discovering what the structure of the atom is. And that will include the discovery of some of the particles that make up the atom, what we call the subatomic particles. We'll talk about atomic number, which is the number of protons, the positively charged particle in the atom. And this is the only thing that determines what kind of atom it is. And the mass number, which is the number of all the particles in the nucleus of the atom, the center of the atom. These are the heavy particles that give most of the mass to an atom. We'll talk about the atomic mass, which is the average mass, you can think of it as weight, the average mass or weight of a typical atom of a single element. We'll talk about the current models of what the atomic structure looks like, and these were actually developed back in 1926, and they still hold up today. Then we'll talk about how the electrons, these are the negatively charged particles in atoms, they are not in the nucleus, they surround the nucleus, they are negatively charged particles that occupy volumes of space that are very large compared to the nucleus. The nucleus is a tiny dot in the middle of the atom, but the orbitals are the volumes of space where the atoms are occupying. And then we'll talk about trends in the periodic table. There are a number of different properties that each of these elements has, and there are clear trends in the periodic table. For example, the size of the atoms as defined as the atomic radius. The smallest atoms are in the upper right-hand corner of the periodic table, and the largest atoms are in the bottom left-hand corner. So that's a trend that we'll talk about. So before we go further, let's talk about what an element is. And an element is a pure substance that contains only one type of atom. In other words, it could have one atom or more than one atom, but it has to be one type of atom, and it can't be broken down any further by chemical means. Now the atom itself is the smallest particle of the element that still retains the properties of that atom, of that element. So if I have a particle of iron, a single tiny particle of iron, an atom of iron, it's still iron. It still behaves like iron. We also have 3 subatomic particles. These are particles that make up an atom. The proton and neutron, which are found in the nucleus of the atom, and these are the ones that give the atom most of its mass, most of its weight. The proton is positively charged, proton positive, P and P, that's easy. And the neutron is neutral, non-charged, uncharged. So neutron, neutral. The electron is the negatively charged particle. So remember, this one's a little harder to just straight remember from the letters of the abbreviations. But electron is the negatively charged particle that forms the cloud surrounding the nucleus of an atom. The electron has very little mass, but most of the volume of the atom is with this electron cloud. We have the atomic number, this is the number of protons, and the mass number, that's the number of protons plus neutrons, which gives you an idea of the general mass of the atom, of a particular single atom. This is not exactly the mass, it's just a quick way of calculating roughly the mass of the atom just by adding up how many protons and neutrons, because they weigh about the same, they have roughly the same mass, and you just count them up. Isotopes are atoms of the same element, which means they have the same number of protons, because that's the only thing that determines which element they are, but they have different masses. And the only way to get different masses is to change the number of neutrons. So we have atoms of the same element. For instance, hydrogen can have 1 proton and no neutrons. That would have a mass number of 1. 1 plus 0 is 1. And hydrogen 2, which has, that's the isotope 2 of hydrogen, that one has 1 proton and 1 neutron. So its isotope number or mass number would be 2. And then we have hydrogen 3, which has 1 proton and 2 neutrons, for a total of 3 heavy mass particles in the nucleus of that atom. The atomic mass is the average mass of all the atoms for a particular element. So if there are different isotopes within the same element, you have to average all of them up, and there's a mathematical way of doing that we'll talk about, to get the average mass of a typical atom of, say, iron or cobalt or hydrogen or tin. So here's the periodic table, and I've got it color-coded here. This color code will come up in a later slide, but the color code represents some behaviors of the elements. And let's talk first about the periods of the periodic table. The periods, as I mentioned, are the horizontal rows of the periodic table. They're called periods because the properties of the elements repeat one another as you go below. So an element, say number 3, lithium, Li, that's the first reddish pink one here, has very similar properties to sodium, Na, because the properties of the elements as you go in increasing order of protons, and that's how these are numbered, by the way. They're numbered from 1 to 118 in order of how many protons there are, or in order of the atomic mass. So if we go in order, you'll notice that lithium, and then 8 atoms later, you get to sodium. Well, sodium has a similar properties to lithium. And magnesium, Mg, has similar properties to beryllium. In other words, the properties repeat periodically, hence the name periodic table. The vertical columns are called groups because atoms within that group tend to have similar properties. So they're organized by the atomic number, the number of protons. The rows are periods, the groups are the columns, and atoms within the column have similar chemical properties and reactivity towards other chemicals. Let's look at the history of the periodic table. Years before the first periodic table was even conceived, a man named Johann Derbyreiner, German scientist, noticed that when he looked at various elements, remember there were only lists of elements in those days, he noticed that there were groups of 3 elements that he could find, an element here, an element there, and an element there, where one element had a mass, had an atomic weight that was almost exactly midway between 2 other elements. Well, what he discovered were groups, the vertical columns. He noticed that, for example, calcium and barium, they're in the second column that I just showed you in the periodic table, Ca and Ba, and right in between them is an element called strontium. Well, we know that now, but at the time, he noticed that strontium's mass, its atomic weight, was halfway between calcium's and barium's, and these were called Derbyreiner's triads. Now, about 40 years later, a man named John Newlands, a British scientist, created one of the first periodic tables, and he wasn't really giving much credit for this because that went more to the man that's next on this list, Dmitri Mendeleev, in 1869, only 4 years later, who didn't even know about Newland's work. But Newland noticed this repeating pattern of every 8 elements, that they would have the same properties, similar properties, and he noticed this if he organized them in order of their mass, and this was called the law of octaves, octave meaning 8 notes in a musical scale. In this case, it was 8 elements. Then Mendeleev, who made many of the similar discoveries, he made his own periodic table. Newland actually arranged his groups horizontally and his periods vertically. Mendeleev did his the other way around, which is more similar to the modern periodic table. But he noticed when he created his periodic table and lined the elements up by their properties within each group, he noticed there were spaces that weren't filled with any element that was known. So he actually made predictions for quite a few elements that were unknown that were eventually discovered to fill in those spaces. So that really showed the power of his table. And years later, a young man named Henry Moseley, he was only 26 when he did this work, and he was one of the pioneers in X-ray analysis of atomic structure. And what Moseley noticed as a young man was that the periodic table, which had always been organized by atomic mass. Now remember, I told you the modern table is organized by atomic number, the number of protons, but in those days, when Newlands and Mendeley were doing it, they didn't know about protons, so they organized it by how heavy each element was, the atomic mass. Well, when they organized it by that, they just numbered them from 1 to whatever. It was about 50-some elements at the time. They didn't know the numbers meant anything. They were just writing them in order of the appearance in the periodic table. It was Moseley who discovered that those numbers actually meant something. They were actually the number of protons, and he discovered that from his X-ray analysis. And that led to the modern version of the periodic table numbered by by atomic number, the number of protons. Unfortunately, Moseley, who was this incredibly brilliant young man, he was also very patriotic. So when Great Britain went to war during World War I, he enlisted and was unfortunately killed in the Battle of Gallipoli. He was shot by a sniper and died. And it is thought that the Nobel Prize in Physics in 1916 went to no one because it should have gone to Moseley, but unfortunately Nobel Prizes can't be awarded to people who have already deceased. So the periodic table can be broken up in a number of different ways, and we'll talk about several of these ways to look at the periodic table. One way to group it is what we call in the Group A and Group B family of elements. And the Group A are shown in yellow, and these are the columns, the first, second, 13th, 14th, 15th, 16th, 17th, and 18th column. It's 18 columns wide, so it's the first 2 and the last 6. These used to be referred to as the Roman numeral 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, 8A, and that's why they were called the Group A elements. They were numbered from 1 to 8 with the A using Roman numerals. We also referred to these as the main group elements because a lot of the original chemistry that was discovered about the elements was discovered using the Group A elements. They're also referred to as the representative elements, so that term is going out of vogue. We also have the blue elements, which are the Group B elements. So there are 2 clear sections here as well. Groups 3 through 12 represent the transition metals. They're called the transition metals because they transition between the first part of the Group A and the last part of the Group A. They're in between. We also have the other groups down at the bottom. You'll see the 2 rows in blue. These are now called the lanthanides and the actinides. They're named for the first element in each row. Lanthanum, number 57, so that row are called the lanthanides, and actinium, number 89, that row is called the actinides. And these also used to be called the intertransition elements. They used to be frequently referred to as the rare earth metals, though people don't use that term so often because a lot of these metals have been found in large mine deposits in China. And uranium, number 92, is actually found many places around the world, especially in the United States. So now we call them the lanthanides and actinides. Another way to look at the periodic table is to break it up into 3 giant sections. The ones in gray that are the metals. And you'll notice metals represent the vast majority of the periodic table. About 90 of the 118 elements are metals. And so the rest of the table are not metals. And those are broken up into the non-metals, shown in that light brown or taupe color. These are the ones that behave very differently from metals. And so metals tend to be, they have properties like they conduct electricity very well. They can be hammered flat because most of them are solids, with the exception of number 80, mercury, Hg. That's a liquid at room temperature, the only metal that's a liquid at room temperature. But these metals tend to be able to be hammered flat. They tend to be able to be made into wires, so they're ductile. That's what makes them metals. Also, they tend to form positive charges by losing electrons, and we'll talk about that later. The nonmetals tend to do the opposite, or they're not very reactive at all. It depends. So if you look at all the nonmetals, including hydrogen over there on the left, the nonmetals can be solids, but they also can be liquids. They could be gases, depending on which one it is. The only liquid in the nonmetals is bromine, Br number 35. All the elements on the far right, the last column, column 18, those are called the noble gases. They don't tend to be very reactive, but the others can typically form negative charges when they're reacting to make compounds, or they don't form charges at all and they just share electrons with other atoms. The ones in the middle, these the metalloids, also called semimetals, are sort of halfway between metals and nonmetals. They sometimes are conductive. They are all solids at room temperature. They behave like metals under certain circumstances, and in fact, most semiconductors are made using these semi-metals or metalloids. One other thing I want to point out, the lanthanides and actinides, you'll notice, actually slip in between the the group A elements on the left. So if we look at barium 56 and radium 88, you'll notice there's a big jump between barium and the next element in the periodic table, and radium, number 88, and rutherfordium, 104. Well, you see that there are all these elements down at the bottom. They're actually stuck in there, and they make the periodic table much wider. If we shove them in there, it would spread everything out. And the reason why they're kept in the bottom is nobody wants to use incredibly long pieces of paper to represent the periodic table. So those are pulled down at the bottom. When they were discovered, we kept them separate, but they really are part of the periodic table. They're just hard to draw on a normal piece of paper. And another way to look at periodic table is to look at specific families in the periodic table in terms of their groups and group names. Now, many of the groups have names. You are responsible for 4 specific group names. Shown in red are the alkali metals. Alkali metals, these are all the group 1 elements except hydrogen. Hydrogen is not a metal, though some people think that if you put hydrogen under high enough pressure, as in millions of tons of pressure, it might turn into a metal, but for now it's not a metal. All the elements in group 2, what used to be called 2A, are the alkaline earth metals. So these are similar names, but somewhat different types of metals. Please don't confuse those. We also have the transition metals in light gray, and that's that block that's 10 elements wide, and right now 4 rows down. Four of the periods have transition metals. They transition from the left half of the group A to the right half of the group A. But there are other metals besides these 3 groups of metals I just mentioned, the alkaline metals, the alkaline earth, and the transition metals. There are metals down at the bottom that I've already mentioned, the lanthanides and actinides, and there are metals just to the right of the transition metals, but before that dividing line of semi-metals or metalloids. Those are the post-transitional metals, or the post-transition metals. They include aluminum and tin. Tin is Sn, number 50. And lead, number 82, Pb. These are named after their ancient names, stannum for tin and plumbum for lead. The ancient Romans made their pipes out of lead, plumbum, and that's why we call the pipes that carry our water plumbing. So we have the metalloids. That divides the periodic table into 3 groups. The metalloids are somewhere between the metals and the nonmetals in their behavior. And then we have a lot of different nonmetals. We have the other category, which is in green here, but they're not the only nonmetals. We also have the halogens in yellow. This is the group 7A, what used to be called 7A in Roman numerals, or now 17. These are these all have very similar properties, and they have similar chemical reactivity as well. And then the last column are the noble gases. They're noble gases because they don't associate with many other elements most of the time. In other words, they don't make compounds with other elements very often. It's extremely difficult to make those. And then, of course, the lanthanides and the actinides at the bottom. And with this, we'll stop here, and we'll start up on the next module.